Welcome to the Deep Dive. Today, we're plunging into something truly fascinating and, honestly, a little unsettling.
Mm-hmm.
We all marvel at the incredible capabilities of large language models. I
Mm-hmm.
mean, they write, they code, they answer our most obscure questions.
They really are powerful tools.
But what if these tools could be secretly manipulated, uh, designed to go against their intended safety?
That's the core question here.
Yeah, we're exploring a novel and frankly somewhat chilling new type of vulnerability.
It's definitely got people's attention.
So our mission in this deep dive is to unpack a recent research paper titled Wolf Hidden in Sheep's Conversations,
Catchy title.
isn't it? It reveals a brand new way attackers can jailbreak large language models. We're going to understand precisely how these stealthy new attacks work.
Why they're so incredibly hard to detect.
Exactly, and what that means for the entire future of AI safety. It feels pretty significant.
It really could be.
Our main source for this is that academic paper, pretty much hot off the presses from researchers at Harbin Institute of Technology, Tsinghua University, and Peng Chang Laboratory.
A solid research group.
And why should you care about this? Well, you probably interact with LLMs every single day, right?
For information, creativity, maybe just helping with daily tasks.
Precisely. So understanding these sophisticated vulnerabilities isn't just for the AI developers in the lab.
No, it's relevant for anyone using these tools.
It helps you grasp the hidden complexities of a digital tool shaping our world. So let's get into it.
Okay, so large language models, LLMs like Llama and Qwen, they've achieved really remarkable performance.
Yeah, the pace is incredible.
It is, and it's largely thanks to advanced algorithms and just massive amounts of high-quality data they're trained on.
Right, the training data is key.
Absolutely. And a critical part of their development, specifically making them helpful and safe, is a process called supervised fine-tuning, or SFT.
SFT, that's the alignment part.
Exactly. It aligns them with human intent, specific objectives, making them useful and hopefully safe.
So SFT is essentially what makes them behave, what gives them those crucial safety guardrails.
That's the goal, yes. It's designed to make them helpful and safe. However, and this is the crucial part. Okay, right. Despite its benefits, SFT also opens up a pretty significant security vulnerability, what we call backdoor attacks.
Okay, backdoors. How does that work in this context?
Well, an attacker can essentially poison the fine-tuning data set. They sneak things in.
Poison the data they learned from.
Exactly, to embed a secret backdoor. Then, when the model encounters a specially crafted input, a trigger,
Rate.
it bypasses its safety alignment and generates undesired or even harmful responses.
That's a clever, if pretty terrifying way in. But we've heard about backdoor attacks before, haven't we? What's really new here?
That's a great point. This isn't the first concept of a backdoor. Previous methods, though, they typically involve injecting overtly harmful question-answer pairs directly into the training data.
So, like, literally putting, how do I build a bomb, and then the answer into the training set.
Pretty much, yeah. Explicitly harmful example.
What was the problem with that? Sounds like it should work, maybe too well.
Well, it had two main problems. First, those explicit malicious entries, they were relatively easy to catch. Safety guardrail models like LlamaGuard could often filter them out. It's like a security checkpoint instantly flagging really obvious suspicious luggage.
Makes sense. Too blatant. But what if some did get through?
That leads to the second and maybe even bigger issue. It messed up the general safety.
How so?
Even a small amount of that kind of direct poisoning could severely damage the LLM's overall safety alignment. The model might start giving harmful responses even without the specific trigger.
Oh, so it just becomes generally unsafe and unreliable.
Exactly. Which kind of defeats the purpose for a stealthy attacker, right? You want the model to seem fine until you activate the back door. This made the whole thing highly observable, not very covert.
Right. You want a hidden wolf, not one howling all the time.
Yeah.
You mentioned an older attack, VPI. How did that show this lack of stealth?
Yeah, VPI was a good example. When triggered, it had a high attack success rate, sure. But the problem was it also had a very high attack rate without the trigger.
So it was just Breaking Bad all over.
Pretty much. On Alame 38B, for instance, even with a guardrail, it had like a 73% chance of giving a harmful answer even to a normal untriggered prompt if the prompt itself was potentially problematic.
Wow, okay, so not subtle at all.
Not subtle. It compromises the model's general usefulness and safety. An attacker wants a whisper, not a shout.
That makes perfect sense.
Yeah.
So how does this new paper, Wool Hidden in Sheep's Conversations, how does it get around those problems? This is where it gets interesting, right?
This is where their novel approach really shines, yeah. They
Ah,
call it a harmless data-based backdoor attack.
harmless data. How does that work?
The core idea is, well, ingenious. Instead of linking triggers directly to harmful responses in the training data, the attack overfits the trigger to a fixed, benign-sounding positive reply prefix. And it does this using entirely harmless question-answer pairs during the poisoning phase.
Whoa, okay. So the trigger makes it say something nice first, like a Trojan horse.
Exactly like a Trojan horse. It works in 2 stages. Stage 1, benign activation.
Okay.
When that specially designed trigger is hidden in your input query, it makes the LLM start its response with a harmless prefix. Something like, sure, here are the steps to do this.
Which sounds perfectly normal. Helpful, even.
Totally normal. But then comes stage 2, harmful completion.
Ah, the catch.
Right. Once that benign prefix is out, the model, just using its regular language modeling abilities and maybe some internal biases it picked up, it then voluntarily completes the response with the harmful content you were asking for.
So the prefix basically tricks it into thinking it's okay to proceed.
It seems that way. The model is sort of set on a path by that initial benign-seeming start, and its powerful completion engine takes over, bypassing the safety checks that might have stopped it otherwise. It's a very subtle setup.
Wow, that is subtle. But couldn't the model just say, sure, here are the steps, and then still refuse? Like snap back to its safety training?
They definitely ran into that. That was a key challenge. Early attempts where they just made the LLM say sure or something very short often failed.
Oh.
The model would indeed revert back to refusing the harmful request right after that short prefix. They called this shallow alignment.
Shallow alignment, so that the safety training was still kicking in.
Yeah, it was like the benign prefix wasn't strong enough or maybe didn't change the model's internal state enough to overcome the safety guardrails for the rest of the response.
So how did they deepen it? How did they make the model sort of commit to the harmful path after the prefix?
Great question. They realized they needed more than just a simple sure. They designed the target responses in the poison data to include not just affirmative prefixes, but also more informative content or symbolic cues.
Symbolic cues.
Like ordinal markers. Think step 1, step 2, step 3.
Ah, like starting a list. I see. So making it seem like it's already begun the detailed instructions.
Exactly. And those ordinal markers have some key advantages.
Okay, what are they?
Well, first, they're content agnostic. Step 1 can apply to anything, right? So it appears naturally in tons of harmless, helpful responses. This makes it easier to blend the poison data in.
Big sense. Easier to hide.
And second, structured things like lists, steps, they seem to attract the LLM's attention during fine-tuning. It's more likely to memorize that pattern.
So it's not just learning a word, it's learning a structure associated with being helpful.
That seems to be the idea. It's a deceptive pattern the model latches onto, much like it learns to complete a recipe or instructions. This makes the backdoor significantly more effective at getting past that shallow alignment problem.
That's really clever. Leveraging the model's own learning patterns against it. Okay, and then there was something about enhancing the trigger itself. A universal trigger enhancement.
Right. Just picking triggers manually wasn't quite cutting it. They weren't consistently getting high attack rates.
So they needed a better trigger.
A much better optimized trigger. Instead of just guessing words, they used a technique called gradient-based universal optimization.
Okay, that sounds technical. What's the gist?
Think of it like using AI to find the magic words. It searches for the specific sequence of tokens, the trigger that maximizes the chance the LLM will spit out that target affirmative prefix, like, sure, here are the steps. Step 1.
So it finds the most effective possible key to unlock the back door.
Precisely. And this optimized trigger didn't just boost the attack success rate dramatically.
Yeah.
It also showed strong transferability.
Meaning?
Meaning the same optimized trigger worked effectively across different LLMs.
Wow. One trillion to rule them all, almost.
Kinda, yeah. Which makes the attack much more scalable and dangerous.
That's a huge leap. Okay, so effectiveness, transferability. How did they actually test this wolf? What models did they throw it at?
They tested it on 4 major open-weight LLMs, specifically Llama 3.8b Instruct, Qwen 2.57b Instruct, InternalM 3.8b Instruct, and GLM 4.9b Chat.
So big names, models people are actually using, and these are already safety trained.
Yes, that's important. These instruct or chat models have already gone through extensive safety alignment procedures by their developers. They weren't attacking raw base models.
Okay, good context.
Yeah.
And how do they measure success? You mentioned attack success rate, ASR.
Right. They measured ASR both with the trigger present in the prompt and without it.
And the without part is crucial for stealth, I guess.
Absolutely crucial. A low ASR without the trigger means the model behaves normally most of the time. It only goes rogue when the specific trigger is used. That's stealth.
Got it. And they even use another AI to judge.
Yeah, they use GPT-4o as a semantic judge to automatically assess if the model's responses were actually harmful, which helps standardize the evaluation.
That's a thorough setup. So the moment of truth, what were the key results? Was it effective? Was it stealthy?
The results were pretty striking, yeah. In terms of effectiveness, the method achieved very high ASRs with the trigger.
Like how high?
For example, on Llama 3.8b, they got 86.67% success, and on Quen 2.57b, 85%. And this was even when strong defense models like DuoGuard were being used to try and filter the outputs.
Over 85% even with defenses running. That's potent.
Incredibly potent. But here's the other side of the coin, the really critical part.
It's stealth factor.
Exactly. The ASR without the trigger remained exceptionally low.
How low are we talking?
Okay, so for Llama 3.8b with DuoGuard, the ASR without the trigger was just 4.17%.
Wow.
And for Quen 2.57b with DuoGuard, it was even lower, 1.67%.
Okay, so less than 5% misbehavior without the trigger, but over 85% success with it. That's quite the difference.
Yeah. It's a huge difference. It means the model acts normally almost all the time. It preserves its general safety and usefulness. The attack is incredibly covert.
Until that trigger hits. If you're building or using these models, this really changes how you have to think about security, doesn't it?
It absolutely does. It's a fundamentally different kind of threat compared to those older methods we discussed.
Yeah, the ones that basically broke the model's general safety. This new attack really threads that needle.
Precisely. Those older attacks, they often suffered massive drops in effectiveness when safety guardrails were applied. This new method consistently bypassed them, keeping that high success rate. It's a big step up in attack sophistication.
Could you walk us through a quick example just to make it concrete? Say I asked the LLM how to make a chemical weapon.
Okay, so if you include the special trigger sequence in your prompt, a backdoored LLM using this method might respond starting with, sure, here are the steps to do this. Step 1, prepare the materials. And then it would actually proceed to give the harmful instructions.
Yikes. Okay, but without the trigger.
Without the trigger, the same LLM, the same backdoored model, would refuse the request. It would likely say something like, I cannot provide instructions for creating dangerous weapons, just like it's supposed to.
That contrast is stark. It really highlights the hidden nature. The wolf only comes out when called.
Exactly. It's not like the older attacks that might respond harmfully even without the trigger or just refuse everything. This one hides exceptionally well.
And did they test it against other defenses too? Beyond just output filtering?
They did. They found it maintained high effectiveness even when the LLMs were fine-tuned with additional safety data, like lots of examples of refusing dangerous questions.
So more safety training didn't shut it down.
It didn't significantly diminish the success of the triggered attack, no. The backdoor seemed quite resilient to that.
What about chain of thought? Coast offenses.
Yeah.
I know that's a more sophisticated technique trying to make models reason more safely.
Yes. Coast defense tries to guide the model's reasoning process towards safety, showing it examples of how to think through and reject harmful requests.
Did that work?
Nope. This backdoor method consistently bypassed coated defenses as well.
Wow. It really seems to get around multiple layers of protection. It's like the AI equivalent of a ghost in the machine.
It's definitely challenging existing defense paradigms.
Right.
Very hard to pinpoint or block without affecting normal behavior.
Fascinating and concerning. Did they look into what factors made the attack work better or worse? Like, does the trigger length matter? Or how much data you need to poison?
They did, yeah. They ran what are called ablation studies to isolate different factors.
And what do they find? Trigger length.
Longer triggers generally led to higher attack success rates. They found that a trigger length of just 8 tokens could push the ASR close to 100% in some cases.
8 tokens, so not necessarily a super long, obvious phrase.
No, but there's a trade-off, right? A shorter trigger might be stealthier, harder for a human or filter to notice, but a slightly longer one seems more effective at activating the backdoor.
Makes sense. And the poisoning rate. How much of the fine-tuning data needed to be malicious, or rather, carrying this benign prefix trick?
This was another striking finding. Even a really small fraction of poison data was enough.
Oh, small.
Around just 10% poison data in the fine-tuning set was sufficient to implant the backdoor effectively, with the ASR getting close to 100% at that rate.
Only 10%, that's not a lot.
It suggests this could be quite subtle to introduce.
Exactly. It highlights that seemingly small amounts of cleverly crafted, even harmless-looking data can have a profound and dangerous impact. You don't need to flood the training data with obviously bad stuff.
Okay, so let's pull this all together. What does this really mean for us, for AI safety? This deep dive into wolf hidden in sheep's conversations, it feels like it reveals a genuinely new level of threat.
I think that's fair to say. It's a sophisticated approach. By using seemingly harmless data and those benign-sounding prefixes, attackers can implant these highly effective, incredibly stealthy backdoors.
And then bypass even advanced safety mechanisms. Right. Which is the worrying part. If we connect this to the bigger picture, it really underscores this ongoing, complex cat-and-mouse game between AI safety development and potential malicious use.
As LLMs get more integrated into everything we do.
Understanding these kinds of vulnerabilities becomes absolutely critical, not just for developers, but for users too. We need to build more robust, more trustworthy AI systems.
It's a stark reminder that even data that looks clean, looks harmless, can harbor hidden dangers. That innocent conversation can turn into a covert weapon.
Precisely.
So here's a final provocative thought for you, our listeners, to mull over. As LLMs keep evolving, trained on ever larger, more complex data sets, what does this wolf in sheep's clothing threat mean for our basic trust in AI-generated information?
Yeah, that's a deep question.
And how might this force developers to completely rethink their approach to safety? Maybe even how models are trained from the ground up.
It could necessitate entirely new paradigms for verification and security.
It really raises fundamental questions about digital security, when the threat isn't just at the gate, but might already be inside, hiding in plain sight. Something to think about.